Hi students, welcome to the session on finding magnetic field due to straight current carrying conductor of finite, semi-infinite and infinite length, right, using BIOT SAVART law. So by using BIOT SAVART law, what we are going to do is, when current flows through a conductor, which may be of finite length or infinite length or semi-infinite length, what is the magnetic field produced? That's what we are going to find, right? So what is a current carrying conductor? Simply it is nothing but our wire. So when current flows through a wire or any conductor, what is the magnetic field produced? What is the expression? That's what we are going to derive in this session, right? Okay, let us assume that here the current carrying conductor of length AB. This is what here to here, right? So this is our current carrying conductor AB, right? I want to find what is the magnetic field produced. Let us assume the current flowing through this I. We want to find what is the magnetic field at this point P. This is field point, the point where we are finding the field. So P is a field point, right? As per BIOT SAVART law, what we do, instead of finding the magnetic field produced by total wire, what we do, we take one small segment. From that, we find what is the current produced by that small segment. Then we take another small segment, then find it. Then we take another small segment, and finally we add all the magnetic field. The same procedure we are going to follow here also, right? So where I kept my conductor, it is kept in the z-axis, right? Conductor is kept at z-axis, right? And the distance between the small current element to the field point is, we can call that is R, and angle between DL and R, angle between DL small current carrying element and R vector is theta, right? Angle between the lower end of the current carrying element to the field point is theta 1, and upper end of the current carrying conductor to the field point is theta 2, right? So assume that we are assuming the current is flowing from A to B, that is lower end to upper end, sorry, fine. So I flows from A to B, right? So theta 1, theta 2 and all we know. Right now, as per the BIOT SAVART law, right? So where this DL is there, let us assume it is located at z-axis. So 0, 0, z. I don't give the value for length. It is simply located in z-axis. x0, y0, z0. So the magnetic field produced by point P due to this DL is given by, as per BIOT SAVART law, dH is equal to IDL cross R cap divided by 4 pi R square. Fine. Okay. Right. So from this, what I need is, I need DL and R vector. Right. So you see that I can write as R cap, I can write as IDL cross R. R is a unit vector I can write as R cap divided by mod R. Mod R is nothing but R, so 4 pi R squared into R, 4 pi R cube, right? Now we will see, right, here R is, capital R, right? Everything is capital R, so simply use capital R, that's not issue, right? The distance is capital R, not small r, right? Okay, so what is my DL? DL is a value which is, DL is in z-axis, so any vector can be written as its magnitude. What is the magnitude? The length of the current carrying element, it is in dz, so small length along dz. In which direction? Az direction, z direction. So I can write dl as dz az. The magnitude of this current carrying element I take as dz multiplied by unit vector. Any vector can be represented in terms of magnitude and its unit vector. So this is important point. So now I find R value, R cap. R cap is given by, you see, it is given by R comma 0 0 minus 0, 0, comma z. Why? R is the distance between the field point minus source. What is the distance? It is, right? Okay, so it is in rho direction, right? It is a we assume that it is a spherical coordinate system. In spherical coordinate system, it is in rho direction. So rho pi z is a coordinate. So rho phi z. So assume that we are working with the spherical coordinate system. Please remember. Alright, that's why I put the rho, right? So it is a rho or r. So I take rho value is r. So r. So in which direction? So it is rho phi z. So it is in rho. Actually, this is rho. No, this rho we know that this is rho. I kept here. So this is also rho only. So total circle the same distance, right? So this distance is r. Instead of rho, I use r. So r comma 0 comma 0, right? So that point is r comma 0 comma 0, right? Next, what about this point? Source point is 0 0 z, right? So what happens? So it is in rho in vector. It is in rho direction. So how can I write? R into arrow pi and z are 0 minus z component only, z into az r cap, right? So clear? So this is short. Why I am writing r cap like this? For the reason is I have given, right? So r vector is equal to r into arrow minus z into az. Okay, now we got dl and r. Now we substitute h is equal to I, right? Dl cross r cap divided by 4 pi r squared or 4 pi r cube. Here r, oh sorry, here r vector, r vector, right? So dl I found, r I found, dl cross I need, dl cross r vector, right? Dl vector r vector, dl is dz az, right? Cross r arrow minus z az. If you take cross product, az 0. So r dz, az arrow a phi. So az cross arrow a phi. So dl cross r is r dz a phi. So now substitute this in BSL equation. So ideal cross r, I into, instead of dl cross r, I substitute r into dz, right? 4 pi, right? A phi. In denominator we have r cube, right? So r cube we have to find. First, in order to find r cube, we need to go and see this is r, capital R, right? This is capital R cube, right? So capital R cube I want. First I want magnitude of R vector is vector. What is the magnitude? Mod R. Magnitude of R is equal to R. You see, this is given by, this is a triangle. If you take this triangle, this one, what is that? It is hypotenuse. So I use Pythagoras theorem. This length is R, this length is small r, right? And this length from here to here, we know that 0 0 is z, right? So we can say r is equal to r squared plus z squared. Simply you take this triangle. Here it is r, this length is r, this length is a. Here only we are having that dl, right? So hypotenuse squared is equal to root of hypotenuse is equal to root of adjacent squared and opposite squared, right? So okay, then r is root of z squared plus r squared. So r is equal to r cube I want. R is equal to root of z square plus r square, root I write as 1 by 2 r cube, so cube. So that will be I r dz divided by 4 pi r square plus z square into 3 by 2 a phi. Okay, then from the diagram we find cot phi. Why I find cot phi you will understand quick. Cot theta. So cot theta is equal to, from the diagram you see cot is, tan is opposite by adjacent, cot is adjacent by opposite. So what is my adjacent? My adjacent is z, this length. This is theta. Cot is adjacent by opposite. So z by r. So cot is z by r. So z by r. This implies z is equal to r cot theta. I want dz. That's why I found cot theta. So dz is equal to, cot theta is minus cosecant square theta, differentiation. So minus r cosecant square theta d theta. So dz we found, right? Next we substitute here. So what is that? I minus I by 4 pi is constant. I is a constant, 4 pi is a constant. Where is the angle? Angle goes from, okay, let us see, theta 1 to theta 2. Why? We have to do integrate with respect to theta 1 to theta 2 because we have to see from A to B. So what is the angle here? Theta 1. What is the angle here? Theta 2 with respect to field point. So I have to find, I should not leave it only this dl. I have to take another dl, another dl, another dl, and totally I have to integrate. So angle varies from theta 1 to theta 2. So this is the thing, theta 1 to theta 2 I am getting. Then what I do? Okay. My equation is I into I take an outside r dz, r into this minus I brought outside, instead of dz, r into r square cosecant square theta d theta a phi. In dz I substituted this minus r, minus came out, r into r square, right? Okay, bring 4 pi, so 4 pi I have taken outside, so okay, divided by r squared. R is nothing but r cot theta. So r squared cot squared theta plus right. So sorry, z is equal to r cot theta. So r squared cot squared theta plus r squared. Right. This is my z. So if you simplify, what happens? I can take outside minus I by 4 pi. A phi I taken outside, a phi, then theta 1 to theta 2, r squared cosecant square theta, here it is 3 by 2, right? So cosecant square theta d theta divided by, right, r squared I can take commonly outside, so r squared into 3 by 2, so it is r cube, so r cube will come outside, right? So remaining thing will be 1 plus cot square theta, that will be cosecant square theta, that will become cosecant cube theta, right? So if you have any doubt, what is that? R squared cot square theta, r squared cot square theta plus r square, you take r square outside, 1 plus cot square theta, right? 3 by 2, 3 by 2. Right, r square 1 plus cot square cosecant square theta 3 by 2. So r square into 3 by 2, 2 into 1.5, 3. Similarly, cos square 2 into 1.5, 3 by 2 is 1.5. So cosecant square, cosecant cube theta. So that's what I have written here, right? So what happens? This cancel, cosecant square, cosecant cube will be cancelled. So minus I by 4 pi a phi theta 1 to theta 2, 1 by cosecant theta is nothing but sin theta d theta. That is what my h vector. right? So from this, H is equal to, okay, in denominator we have one R, this R is there, right? This R is there, that R I bring outside. So 1 by 4 pi R, sorry, I by 4 pi R minus sin theta is minus cos theta, theta 1 to theta 2, right? If you simplify, minus you take outside, so it will become H is equal to I by 4 pi R cos theta 2 minus cos theta 1 into, sorry, A phi is here, so A phi. This is what magnetic field due to finite length conductor. Finite length current carrying conductor. Suppose in exam if they ask up to this, you stop here. If they ask infinite length, you find that. Or semi-infinite, you find that only, right? Okay, next what we have to do? We have to find for semi-infinite length. So what is the magnetic field due to semi-infinite? Right? So H due to semi-infinite. We know that our actually this is what we had, right? Our conductor was here from okay. I draw somewhat bigger. Okay. So we draw somewhat big. So what happens? Our conductor A starts here and ends here, right? This is what theta, right? And we have found a P here, right? This is theta we know, right? Now it is semi-infinite. Semi-infinite means this is theta 2 we know, right? So this is at theta 2, this is theta 1, right? So what we are going to do is, this is what finite length, right? So you see again, I show this. You see theta 2 is here, theta 1 is here, the length A to B, right? So now what we are going to do is, we want to make it as infinite. So it has to start from 0 and go to infinity, right? Already this distance is theta 2. Once it is going here, it will become theta 2. Theta 2 will become, this point will go to infinity and this point will go to 0. Then only total length is infinity. That means A should go to 0, B should go to infinity. So what happens when I make my length of the conductor is semi-infinite, A should go to, A should go to 0 here and B should go to infinity. So A will be at 0, 0, 0 and B should be at 0, 0, infinity, right? So here already theta 2, we start from here, so it is 0, angle 0 degree means now A comes here, it is perpendicular to the point, so the angle is 90 degree. So what happens, the angle theta 2 will be 0 because we are starting from here, right? Okay, so we are starting from here, from for one line, if you start from here, it is 0 degree means it is 90 degree, right? So this is theta 1, now theta 2, this is theta 1, this is 0 degree, this is 90 degree. So theta 1 becomes 0 degree, theta 1 becomes 90 degree. Now if you for this is the condition for semi-infinite. So we know finite length, in that if you substitute theta 2 0 and theta 1 90, what happens? You substitute theta 2 0, theta 1 90 means cos 90 0, cos 0 1. So it is I by 4 pi r A phi, right? So the magnetic field is H is equal to I by 4 pi r A phi. This is magnetic field produced due to semi-infinite length current carrying conductor. Now next what we have to do, H due to infinite length. Infinite length means minus infinity to plus infinity. So now point A should go to negative infinity. So now A will be at 0, 0, minus infinity, and B will be at 0, 0, infinity. So B already at the same position. So here angle is 0 degree, means what is the angle at A? Exactly opposite. It starts from 0 and max here it is 0, means here it is 180 degree. This is 90 degree. We know that. So now theta 2 is 0. Theta 1 is 180 degree. So theta 2 0 degree. Theta 1 is 180 degree. Now H is equal to, if you say H is equal to I by 4 pi r cos theta 2, cos 0, 1 minus cos theta 1. Theta 1 is 180, cos 180 is minus 1, minus minus plus a phi. If you simplify, what you get is H is equal to I by 2 pi r a phi. This is what magnetic field generated due to infinite current carrying conductor. So here you see we have to conclude some important points. Conclusion. Right? So what is that? Here H depends on magnitude of H. Magnitude of H depends on R. What is R? R is the distance between the origin and field point. This is what we know R, right? So it depends only on the distance between the source and center of the source and field point, right? That is the first thing we have to remember. Second thing is very important. You see, direction. It is depending on only a phi. We know in spherical coordinate system, this is R. Phi varies from 0 to 360 degree, right? So it is going like this. Phi. It is complete 0 to 360 degree. So this a phi complete circle. So magnetic field will be rotating, right? It is rotating. Phi is phi. What is the value of phi? Phi varies from 0 to 360 in spherical coordinate system. So you see, this H is rotating with respect to phi. Unit vector is phi. This phi varies from 0 to 360 degree. That means this H will be rotating. So when current rotating magnetic field. So what we conclude from here, when current flows through a conductor like this, it will create rotating magnetic field around the conductor. That means, now you remember, whenever you see a wire in your home, when current flows through that, there is a magnetic field rotating around that wire. That is very important. That's what this A phi indicates. Right? So this is very important conclusion. So when current flows through a conductor, it will create a rotating magnetic field. Right? So like that, we see another one important point. So rotating magnetic field means I draw exact circle. I hope I am trying to draw exact circle. Right? Here you see from here the distance, let us assume this distance is R. If this is R, this is also R because it is circle. Okay, it is right. This distance is R. This distance everywhere it is R. All the points on this loop is circle is R. That means everywhere the magnetic field is same because H is equal to I by 2 pi r. I is a constant. Here all over the circle the distance from the center is R. So R is also constant. 2 pi is a constant. So if you find magnetic field here, if you find magnetic field here, if you find magnetic field here, all will be having same magnetic field. So it produces uniform magnetic field. When current flows through a conductor, it produces uniform magnetic field at a fixed distance from the R. Fixed distance R from the wire or conductor, right? So if you draw a circle around your wire, all through the circle the magnetic field will be having a same value, right? How it will be appearing like that? So if it is a current carrying conductor or wire, then current flowing through this, right? I see how the magnetic field will be. It is a rotating magnetic field. It is like this, right? So it will be rotating. Okay, so this is small like that, right? Rotating. So why it is coming out from this and going in this arrow direction? I have explained it in BIOT SAVART LAW session, right? So I hope you understand everything clearly. If you are having any doubt, please ask me in comment section, right? So another point I want to emphasize is H is independent of phi and Z. H is independent of Z, magnitude of Z, right? What is mod H? Mod H is magnitude I by 2 pi R. Magnitude of unit A is a unit vector 1. So you see magnitude of the magnetic field is independent of pi, independent of Z. It depends on only rho or R, right? So magnitude H depends only on R and independent of phi and Z. So it depends only on R or rho. So in spherical coordinates, it depends on rho only, magnitude, but direction depends on phi, A phi. That's why it is creating rotating magnetic field. Right? I hope you understand everything clearly. If you have any doubt, please ask me in comment section. Thank you.